Hello, everyone. Can you hear me okay? All right, great. So, my name is Charlie. Thank you for the introduction. And today I'll be talking about my project, Sunflower, locating underwater robots from the air. Fidel, thank you so much for your talk on many different ways, but one of the ways that really helps me is that you introduced this idea of underwater robots and things in the air and talking between the two of them. So, as we saw before, underwater robots are a really important tool for various applications, including underwater monitoring, etc. But one of the fundamental problems is knowing exactly where these robots are in the world. We might think, all right, let's use GPS, but as, again, saw before, those GPS waves are going to attenuate extremely quickly because they're using RF frequencies for those communication, which really means we cannot use GPS underwater. And because of that, state-of-the-art is going to use acoustic positioning. So underwater, we're going to use acoustic waves, and we're going to first deploy on the surface some sort of relay system, so maybe a boat or a couple buoys. And then again, underwater, use acoustic waves, and then in the air, we're going to use something like Wi-Fi to actually perform that coordination. And while this works, the main issue is that it fundamentally constrains the sensing area to where our surface relays are located, which again limits the practicality of all of these systems, which would really benefit the world if we could get them working and if they could become ubiquitous. So in this project specifically, we're curious if we could use the flexibility and mobility of an aerial drone, which has kind of a bird's eye view across the entire situation, and really leverage their mobility to reduce that overall sensing overhead. And we do that with our project Sunflower, which is the first system that demonstrates direct 3D localization of underwater robots using a drone, and it's completely wireless. So let's just jump really quickly into a demonstration here. The drone in the air is going to localize the underwater robot as it moves to 6 different locations. And we can see our ground truth and also the sense locations on the plot here. And we're steering this laser beam, and then the underwater robot is going to retro-reflect it back to the drone, which is going to compute the position, and then it shows up on the map there. And if you look at our little plot, we have a nice S here for MobiSys. So let's take a look at some of the challenges associated with using laser light in this context. First and foremost, we have these weak retroreflections. So we're using backscattered light to send data back from the underwater robot to the drone in the air, which means the light is going to travel twice the typical path length that you would normally see in an optical communication system. And additionally, optical backscatter is going to use polarization, which would incur an additional 50% loss and possibly more depending on the optics that we choose. And then compounding these issues, any practical application of Sunflower would really be in some sort of real-world environment where the solar noise is going to increase our noise floor. We could have an illuminance value on the water surface up to 100,000 lux, which really just makes this challenge of detecting and decoding the retroreflected light that much more difficult. And third, we're using light. I'm sure we're all thinking this. What about refraction? So the light's going to hit our water surface and it's going to refract through, which means we can't simply rely on this angle alpha, which is what we're steering our laser beam with, to compute the underwater robot's location. Similarly, we don't know the shape of the water. We're not doing any additional sensing. And because of that, alpha and beta here are only relative to the normal point on the water surface. And third, we're going to have inevitable oscillations of the value of beta here for a single value alpha because, again, we have that refraction and we're hitting the wave at different points in time. So we solve all of these challenges with various algorithmic and hardware designs. And fundamentally, Sunflower is composed of a worker component, which is going to be underwater, and a queen component, which is going to be in the air. First and foremost, the worker is going to solve the challenge of refraction using its integrated angle of arrival sensor, and it's going to send that data back to the aerial queen over the optical backscatter channel. Second, the queen is going to use its fiber sensing ring to detect those ultra-low SNR retroreflections, and then that's going to be further increased by our laser-optimized backscatter system. So let's first take a look here at our fiber sensing ring. There's a few components that are really required for our queen in the air, again, to steer its laser beam to hit the underwater worker. And if we want to include our retroreflector now on the worker underwater, we see we only have this really small region where we can actually detect that light that's coming back to the queen. And so we have this question, where do we want to put our sensing device? Well, we could put it next to the enclosure, but unfortunately, if the two nodes are rotated or misaligned, we might miss some of that light. And ideally, we'd want to be always within the sensing region, but this would require multiple photodiodes, kind of overall increasing the complexity of the system. But we're using light, right? So let's try to leverage the physics of it. And we do that with our optical fiber sensing ring, which is essentially going to detect those ultra-low SNR retroreflections and divert them above and around our rigid optical enclosure, and then focus it down on the other end to a single photodiode. And not only do we achieve this optimal co-location, but we also can increase our effective sensing area with this design. So we can consider here our transmitter lens next to a single photodiode, and also our optical fiber ring surrounding our transmitter lens. And in the first case, when the light comes back and hits it, we're only covering this 9mm squared sensing area, but with our fiber sensing ring, we could increase that to 35mm squared, which is a 3x increase. And again, we're still focusing that light down on the other end to a single photodiode. Alrighty, let's now take a look at our laser optimized backscatter design. So typically, in Backscatter, we're going to have an LED, we're going to have a liquid crystal modulator, and we're going to have a retroreflector. And the LED will emit its light, which will either be passed or blocked by this liquid crystal modulator. It's going to hit the retroreflector and then bounce back to the LED, where we'll sense it with a photodiode, or in the case of sunflower, our optical fiber sensing ring. And so the left components here will be on the queen in the air, and the right components will be on the worker underwater. Before I move on, though, let's just touch briefly on how these modulators are working. So under the hood, essentially, they're using polarization of the light to modulate it. And typically, light would be unpolarized, meaning its electric field and the energy of the light itself is going to be oscillating in random directions along the path of propagation. Light could be linearly polarized, and this is what you would see through your sunglasses, for instance, if they were polarized lenses. Or it could be circularly polarized, so it's going to oscillate in a circle and along, again, its path of propagation. In the case of an LED, it's emitting unpolarized light. So once it hits the liquid crystal modulator, it's going to pass through this first stage polarizer, which will, again, effectively crop out 50% of the energy. Second, it'll pass through the actual liquid crystal, which will rotate the state between two orthogonal modes, so like up or down, left or right. And then finally pass through another polarizer, which will block the light or pass the light and allow us to modulate that bit. So I'm not sure if we see the issue here yet, but if we have an LED in this backscatter scenario, we're going to block minimum half of the light, again, because we're transforming that unpolarized light to linear polarization. And we're already dealing with very weak retroreflections, so we want to avoid this if all possible. And because of the title, and I previously mentioned, well, we're using lasers, and how would those work as opposed to an LED? Well, the laser is going to be linearly polarized along one axis, and what this would allow us to do is basically eliminate that polarization loss by maintaining a single state throughout the entire optical system. And it sounds great, right? We solved it. One issue, the laser is going to rotate, right? The queen and the worker will move because we want to put this on a drone and a robot. We're going to have mobility. And because of this, we have this misalignment now of the polarization axes, which again introduces this strong loss. To solve this issue, we're going to utilize two quarter wave plates, which are essentially going to convert the linear polarization to circular in free space. And then effectively, the queen and the worker will have a linear polarization. Free space will be circular, meaning we can support arbitrary rotations between the two nodes and also full mobility, while also having that zero polarization loss between the two sides of the system here. And one other thing, we're using frequency shift keying on both ends, which allows us to separate any stray reflection that might come back to the queen from those modulated bits that we're intentionally trying to send. Okay, so our last element here is our angle of arrival sensing mechanism. As I mentioned before, our queen in the air is going to emit its laser light, and it's going to hit the underwater worker. We're going to then sense that light. And then from our depth measurements and altitude measurements, which we can obtain with, for instance, an ultrasonic sensor or a pressure sensor, we can get our first coordinate here. But any additional coordinate of our underwater worker relative to our queen is going to rely on this, these two angles, alpha and beta here. So alpha being the laser steering angle, beta being the angle of arrival. And of course, we have a question, how are we going to get beta? Well, we might think, let's use Snell's law. That might be the go-to here, and we can solve for theta 2. And while this would work in some scenarios, we would need to know the refractive indices of both the air and the water, which again kind of constrains where we can deploy this system to ones where we have prior measurements, so not ideal. But more importantly, alpha and beta are only relative to the normal, so where we hit the wave at any given point in time. And since we're not modeling the wave or anything like that, we can't guarantee that alpha and beta will be equal to theta 1 and theta 2. So instead of trying to compute this angle, we decided we're going to measure this angle. And we do this with our integrated angle of arrival sensor, which is composed of a pinhole mask and a 2D image sensor. So when the refracted light comes through and hits our mask, only a small ray will pass through and hit our image sensor. We can then map the 2D pixel coordinate on that image sensor to our angle of arrival beta. And now let's kind of add this into the overall system here. We have our queen in the air, our origin point. It's going to steer its laser beam, hit our worker. The queen and the worker will measure their altitude and depth, send it back to the queen over that backscatter channel. Queen will measure its two-dimensional laser beam steering angle, alpha and beta. The underwater worker will measure its angle of arrival, again, send that back over the optical communication channel. And finally, we have our components here for the position of the underwater worker in 3 dimensions. And there's one small caveat here, which is that we assume those height and depth measurements all lie on the same plane, but we'll talk about that in a little bit. All right, let's take a look at our prototype. So this is the queen. This is on the aerial drone, and you can see we have our optical fiber sensing ring, which is is surrounding our laser optics module. If we want to zoom in here, I think we might see where we're getting the name sunflower from, based on our laser fiber sensing ring here. It kind of looks like a sunflower from the top. And one end we're doing our sensing, and the other end we're coupling that down to a SIPM array, which is basically our photodiode, and a bandpass filter to block out unwanted light. Next, we have our laser optics module, and there's a lot going on here. Basically everything for steering our beam, focusing it down, converting those polarization states. Like I said, a lot going on. And then finally, we have our worker, and this will be underwater. It is a fully waterproof container, and we can see we've got our custom circuitry inside that supports all of the different backscatter modulation. We have our polarization optics, and we also have our angle of arrival sensing components. Great, let's take a look now at our evaluation. In general, we had 2 main setups. Both were conducted in a pool. And the first one is a semi-stationary setup, meaning the queen was on a tripod and then the worker was on a moving underwater robot. And then the fully mobile setup where the drone had the queen on it, and then again, we're using the underwater robot. To obtain our ground truth, we utilize the UAV, which is going to localize itself underwater to a fiducial marker. This is fairly common in the robotics community, but it does have a large deployment overhead and only works for a few meters. So, it's not a direct competitor to Sunflower, but is really useful for obtaining the ground truth. So first and foremost, we have our accuracy. On the x-axis, we have our error and our CDF on the y. And we compare 2 scenarios here. So with refraction sensing, meaning we're sensing that angle of arrival and using that in our localization context. And then without refraction sensing, just steering the beam, sensing the light, and going from there. And in the second case, we have an error of 20.9 centimeters. Whereas in the first case, with all of the components of Sunflower working together, our error is 9.9 centimeters with a standard deviation of 2.6. And you might be wondering, how does this compare to those underwater-only acoustic-based localization systems? Well, the state-of-the-art ones would say they have an error of about 4 centimeters on their data sheet. But in practicality, many of these systems would have meter-level jumps when you're actually being deployed out in the water, meaning their accuracy is on the level of 100 centimeters. And so Sunflower is doing pretty well compared to both the nominal value and the experimental value especially. Second, we look at the impact of waves. So the queen and the worker only measure the altitude and depth relative to the point directly above or below them, which means that our error will increase as the amplitude of the wave increases, and the rate of that error would increase as the wavelength of the wave increases. So we wrote a simulator to vary the peak-to-peak amplitude on the x-axis and then measure the error on the y. And for amplitudes common to lakes, our error is below 10 centimeters. And for amplitudes common to oceans, our error is below 22 centimeters. But we will discuss some of the ways to improve this even further in our future work. Next, we have our localization range. So on the x-axis and y, we have the depth and altitude of our worker and queen. And as I said before, we need those backscattered packets in order to decode and compute the position of the underwater robot. And because of that, we define our localization range in terms of our packet success rate, or how many of those data packets did we correctly decode and could extract that depth and angle of arrival information. And across all of the distances we tested in our pool, we had a 99% packet success rate up to 3.8 meters joint between the air and the water, which notably is sufficient for various applications today, including shoreline monitoring and also reef monitoring. And finally, we have our fully mobile demonstration. So it was pretty difficult to obtain the ground truth of the drone indoors. This is an indoor pool, I don't know if you can tell. But we figured out a way to do it. And so for our final evaluation here, we have the queen on a drone and then the worker underwater. And throughout this experiment, the illuminance value in the pool was about 23,000 lux. So this is pretty common for a sunny day. We performed this experiment in the spring. And both the drone and the robot were causing waves, which were about 10 centimeters in peak-to-peak amplitude. On the plot over here on the right, we can see our ground truth trajectory, again provided by the underwater robot, and our sensed sunflower locations at those 6 distinct spots. And across all of these points, and after throwing pretty much every practical factor we could think of at sunflower, we have sunlight, we have waves, we have vibrations, we have rotations. Our error was only 9 centimeters on average, with a standard deviation of 2 centimeters, which aligns with our experimental results as well in more controlled settings. So what do we want to do next? We have a lot of things we want to do next, of course. First and foremost, increasing the reliability of the system. So optical blockage is a really tricky issue to overcome if you're looking at any sort of optical communication system. But we've got this really great opportunity to use the mobility of the drone and the robot to overcome any obstacle and find a new path. Also, we could consider using ultraviolet scattering to open up additional optical paths that may or may not have been present initially. Second, we have our sensing range. We're currently supporting meter-level distances between the drone and the robot, but we'd like to increase this to potentially kilometers. And we can do this in a few ways. One, decrease our beam divergence of our laser down to the millirad level, and 2, increase our optical power up to a few watts. Third, we have our tracking speed. Currently, we're limited by the switching speed of those liquid crystal modulators, so we're considering alternative modulators that are faster, but also modulation schemes that are equally as robust as FSK, but are faster than FSK. And then finally, multiple robots. We'd like a single queen in the air to localize multiple underwater robots, and really bring our bee analogy here of a queen and a worker to full fruition. So thank you so much. I'm Charlie. Thank you to all my co-authors. This project took a lot, and I'm really happy to be here today. And yeah, happy to answer any questions.